The first big question in calculus is what is the slope of tangent line, or the instantaneous rate of change of a function? And we've now studied that, and we've seen that that is the derivative. So the derivative gives us that. Well, the second big question is, how do we find the area under a curve? And that comes from something called an integral. And that is the subject of our study for this semester. So let's jump in and see if we can find the area under a curve. So here's a graph of y equals 17 minus x squared. We want to find the area under the graph of 17 minus x squared from 0 to 4. So from x values from 0 to 4. So we're looking to find all of this area under here. Okay? So it's hard to find. It's not a rectangle. It's not a triangle. It doesn't match any area formulas that we might use in geometry. So what we need to do is we need to break it up into something that we recognize, something that we can find the area of. So first thing we're going to do is we're going to break this up into rectangles. And we got to decide how we're going to fit the rectangles under here. So first thing we're going to do is we're going to break it up into something called a right-hand sum, or using right-hand rectangles. So we're going to have rectangles that touch the function on their top right corner. Okay, and so let's draw them in. It looks like this. So we're going to have a width of 1. So we're going to break this into 1 because we want 4 rectangles, and we're going from 0 to 4. So our rectangles, we'll start with this first one from 0 to 1. We're going to climb up until we touch the graph on the right side, and then we're going to make our rectangle. Okay, so there's our first rectangle we're going to find the area of. Then we'll take our second rectangle, and let's get a decently straight line. We'll go up until we hit the right hand. The right-hand rectangle hits that curve right there. And then we'll go up, hit the curve, come over. We'll go up, hit the curve, and come over. Now this is a pretty nice function here because all these come out to be integers. They usually won't, but this is set up nicely. So this, since this is 1, this is, the height is f of 1. And if you plug in 1 to our function, we get 17 minus x squared. 17 minus 1 squared is 16. This is f of 2 in height. That'd be 17 minus 2 squared, 13. This is f of 3, 17 minus 3 squared, which is 8. This is f of 4, which is 1. All right? Great. Now, we need to find the area of these. Well, since they all have a width of 1, all right, we're going to make an expression here. We're going to find the total area. So the area, our approximation, is approximately, they have a width of 1 times 16 plus 1 times 13 plus 1 times 8 plus 1 times 1. Okay, and that's what? 16 plus 13, because 1 times 16 is just 16. And so 1 times 13 is 13, so 29, and 8, that would be 37, and 1 would be 27, 37, 38. Okay? Now, that is the area of these rectangles. So I'll kind of highlight them so we can see that better. All right? So the question now is that an underestimate or overestimate? Is that a close approximation to the actual area under here? Well, it gives us an idea of what the area is, but look at all this white space that we did not find the area of. Okay, so this is what we call an underestimate. Okay, so it's underestimate. And we can actually figure out how close we are because, well, the exact area is 140 thirds, or 46 2/3 there. So if we want to find an approximation or figure out what percentage we have there, we have 38 out of 46 and 2/3. And that comes out to about 81%. All right, so we're on the right track. Well, how can we get this to be a better estimate if we still used inscribed rectangles? So these are what we call inscribed. They're inside the parabola. Well, what could we do? Well, one thing we could do is we could make more rectangles. And so if we made more rectangles, we would have, we could like do twice as many rectangles. And so there'd be a rectangle there. There'd be a rectangle there. There. And so if we used more and skinnier rectangles, we'd fill up more of the area. See that? So more rectangles is the key. More narrower rectangles is the key. And that's going to be the key to finding an exact area eventually. Next, we're going to look at a different way to make rectangles that will give us a little different approximation. Next, we're going to look at another way to make rectangles here. This is the left-hand sum. So the left-hand sum means we're going to draw 4 rectangles because, again, we're just going to break it up into 4 at this time. And we'll call these left-hand rectangles that have a width of 1 because 4 divided by 4 is 1. And the height of each is going to be the greatest value of the rectangle intersects on the left, we should say. Okay? So the left of each rectangle. So again, we're going to break it into 4 because our width is 4 that we're finding the area of. 4 divided by, and we want 4 rectangles. So we're going to go all the way up until the left-hand side hits the rectangle, or hits the function. And we're going to make a rectangle if we can. Okay, then we're going to come all the way up on the left. And that hits here. And then we'll get a rectangle there. Come all the way up to the left for our next rectangle. And all the way up to the left where it hits our function. And there it is. Let's see if we can get that a little better. There we go. Okay, so we get different rectangles now. Okay, and these rectangles, you'll notice, end up outside of the parabola. Okay, so now let's find the area of this. So we'll use the function values on the left. Okay, so there's those. That's our area. Well, this height, this is f of 0. F of 0 for 17 minus 0 squared is 17. And this again is 16 and 13 and 17. What is this? This is 8. Okay, this is a height of 8. Okay, so our area is approximately 1 times 17 plus 1 times 16 plus 1 times 13 plus 1 times 8. And that comes out to be 54. Okay, so is this an over approximation or under approximation? Well, we're trying to get the exact area under the curve, and we've got all this extra space that we accounted for here. So this is an over approximation. So our guess, our approximation is too high. All right. Well, if we compare with this 40/3 here, we get about 116%. All right. Well, another way to do this is to kind of average them out or find the midpoint. We're going to actually call it the midpoint sum. All right. So we're gonna take the lower and the upper, and we're gonna find a point right in between at the midpoint there. All right. So we'll kind of average them out. Okay. So again, we're gonna do rectangles that have a width of 1 because we still want to do 4 rectangles, but we're going to choose the midpoint. So the height will correspond to the midpoint of the subinterval. So if we take this half, we're looking at a half here. This half, if we go on up, where does it hit? It hit the graph. It hits right here. That's going to be the height of our rectangle. This next midpoint hits right here. This next midpoint hits right here. Don't worry about drawing it perfectly, because those are decimal values. All right, and so this is called the midpoint sum. So we have a new approximation, and this is going to be 1 times whatever f of 0.5 is, plus 1 times f of 1.5, plus 1 times f of 2.5, and one more f of 3.5. Okay? So now, what are these? Well, we got to plug all these in. They're not going to be nice, neat whole numbers. So we can actually use our calculator for this here. You can use your TI Inspire, or I'm going to go ahead and use Desmos here because it's a little simpler to show at least. So anyways, we can enter our function there, 17 minus x squared, and we have f of 0.5 times f of 1.5, or plus, sorry, f of 2.5, f of 3.5. And there's our sum. We get 47. You see that there? There we go. That's a little easier to see. So 47 is our sum there. Okay. Now, I didn't put the 1 times in there, which is important. If it wasn't 1, we definitely need those there, okay? But these each have a width of 1, so we'll leave it at that there, all right? So there's our sum 47 we got. So our area approximation comes out to be 47. Well, is that an overestimate or an underestimate? Well, we can't really say, because we got some little gaps that didn't get accounted for, and then we got some extra parts out here. So this one we can't say if it's an overestimate or an underestimate. We can make a guess, but we really don't know. All right? So one last one here. We might think, well, what are some better shapes that we could use instead of rectangles that would fill this in? And one good shape would be a trapezoid. So we could use trapezoids to fill this in, or a combination of rectangles and triangles. But we want to use the same idea where we're taking these intervals and we're moving on up. So a trapezoid is a great idea. And let's try that out. So our last area is a trapezoid sum. Okay? So the area of a trapezoid is, well, a rectangle is length times width. Familiar with that? The area is length times width. A parallelogram has the same base on 2 sides, so the area of a parallelogram is base times height. But a trapezoid, if you remember from geometry, has 2 bases, base 1 and base 2. And to find the area of this, we have to average the bases. So the area of a trapezoid is 1/2 of B1 plus B2. That's an average. It's not the length of the top, it's not the length of the bottom, it's the average times the height. All right? So we have 1/2 B1 plus B2 times the height. Well, what we're going to do here is we're going to draw in these trapezoids like this. We're going to take this right-hand side all the way up to the curve, and we're going to take the left-hand side up to the curve, and we'll make a trapezoid out of it. See how that works? Okay. So, again, for each interval here, we're going to take the trapezoid all the way up to the graph, all the way up to the graph, all the way up to the graph. And this one on the far right here, it looks like it follows a curve, but it's not. My free-handed lines, it looks like a curve, but it's not. So it should be a straight line there. So there's our graphs there, all right, or our trapezoids, if we drew them perfectly. Okay, freehandy doesn't do quite justice there. So let's find some areas. Well, the base 1 and the base 2 are these two heights. Okay? So these heights, once again, this is 17, 16, this is 13, and 8, and 1. So for the first trapezoid here, we'll call this trapezoid 1, trapezoid 2, trapezoid 3, so we can talk about it. For the first trapezoid, we have an area of, well, we can see we got 1/2 times the base 1 plus base 2. That's 17 plus 16 times the height, and the height is 1, plus 1/2 times 16 plus 13 times 1, plus, let's keep going, 1/2. We got 13 plus 18 times the width of 1, plus 1/2. I'm sorry, that's not an 18, that's an 8, huh? Okay, let's fix that up. That's an 8. Okay. And 1/2 plus 8 plus 1. And that's times 1, the width of 1. Okay, so each of these here is the area of a trapezoid. And if we were to do more and more of these, we would, it'd be a lot of work. So we could find these, we could compute these each individually. That's one way to go there. Or it's useful to see, and this will be useful for future stuff, we could factor out the 1/2 and factor out the 1s, which obviously doesn't matter. But if we factor out the 1s and factor out the 1/2, we have all these things left over to be added up, right? Well, that comes out to be 17, and then plus 16 plus 16. Well, 16 plus 16 is just 16. And then we got, I'm sorry, 2 times 16. 2 times 16. And then we have a 13 plus a 13. That's 2 times 13. And then we have an 8 plus an 8. That's 2 times 8. And then we have a single 1. So all these things in the parentheses are what I just put there, okay? Let me bring this over here. All right. So all of that times 1. Okay? Now, we can go calculate this right now, but there's one other kind of cool connection that's useful to see. Watch this. This is kind of clever, and it gets to be useful later on. So if we distribute this 1/2 back out now, it ends up being 17 divided by 2. And then I have 1/2 times 2 times 16. Well, that's just 16. Plus 1/2 times 2 times 13. That's just 13. Plus 1/2 times 2 times 8. That's just 8. Plus 1/2 times 1. Well, that's 1/2. All right? So in the end, after we do a little work, and again, this will be useful later on, so we just have half of 17, 17 halves, plus 1/2. Well, that's 18 halves, also known as 9, plus 16, plus 13, plus 8, okay? And so we have, well, let's see, 9 plus 16 is 25, plus 13 is 38, plus 8 is 46. So we get an estimate of 46, and our exact is 46 2/3, so we're pretty darn close. Let's compare that. And that is like 99%. So that's pretty close. So, and we can tell by looking at it, yeah, that got pretty close. So, a pretty clever way, pretty useful way to use trapezoids. And again, useful to see. All it came out to be was it's 1/2 times the first height plus 2 times these, or in the end, half of the first height plus the second, third, fourth, and then the last one gets halved. Anyways, useful connection to see there if you see the pattern. All right. Well, Good deal. So we had, put all these together. Our trapezoid sum was 46, and our other sums were 38 for the right-hand sum, 54 for the left-hand sum, and 47 for the midpoint sum. Okay? So now this won't always be true, but we could put these in order if we wanted. We got the little typo there, right-hand sum, left-hand sum. Okay, so what's the greatest? Well, the left-hand sum in this case was the greatest. The smallest was the right-hand sum. And if we kind of put these in order, the trapezoid sum, no, let's see, the smallest, medium would be the trapezoid sum, and the midpoint sum was pretty close. Anyways, so we can see that we get the approximation many ways, all right? And so soon we're going to get a way to find the exact. Again, the exact for this will be 140 thirds, and that's using something called a Riemann interval or a Riemann sum. And that's what calculus will do to find the exact area for us. So thanks for exploring area with me, and stay tuned. And soon we'll be able to find the area of the curve exactly by finding a million, billion, trillion little rectangles under there. And that is what we call the integral.